So this video is for section 2.6, and it's just working through a few examples of sketching the graph of rational functions that have slant asymptotes that describe their end behavior. So looking at this first rational function, we can factor the numerator. Remember, a rational function is a ratio of two polynomial functions, and it can be helpful to factor the numerator and denominator as far as possible in the real numbers in order to identify characteristics about their graphs. So we'll have x plus 2 times x minus 1 in the numerator. We can see that positive 3 would make the function undefined. So we need to exclude positive 3 from the domain of this function. So in interval notation, we would write that as negative infinity to positive 3, union positive 3 to infinity. There are no common factors in the numerator and denominator that would cancel. Therefore, there are no holes in this graph. And that domain restriction would actually correspond to a vertical asymptote. At x equals to positive 3. And I'm going to sketch that vertical asymptote using a dashed line at x equals to positive 3. Next, I'm going to identify the x-intercepts by thinking about setting the numerator equal to 0. And since I've already factored the numerator, I can see that there will be an x-intercept at negative 2, 0 and at positive 1, 0. So I'm going to plot both of those points. So negative 2, 0 and 1, 0. The y-intercept we can find from evaluating the function at 0. And it looks like we would get positive 2/3. So 0, 2/3. As our y-intercept. Okay, we have the intercepts, we have all of our points of discontinuity, which just ends up being a vertical asymptote at x equals to 3. So now I'm going to determine end behavior. And to determine the end behavior of this rational function, I'm going to identify the end behavior model, which is the ratio of the terms in the numerator and denominator that have the largest exponent. Because remember, when we're talking about end behavior, we're talking about as x gets infinitely large and infinitely small. So those terms that have the largest exponents will end up dominating the numerator and denominator. So the EBM, or end behavior model, for this particular function would be y equals to x squared over x, which simplifies to just be x. This means that our function f of x will have similar end behavior to the positive sloping line y equals to x. That also tells us that because our end behavior model is a positive sloping line, that a better description of the end behavior of this function would be the equation of its slant asymptote, which we know will be y equals to x plus something. That plus something will identify what the y-intercept would be. And to determine what that plus something is, we need to do polynomial long division to rewrite the function. So when we do the polynomial long division, or actually because we are dividing by x minus 3, you could actually use synthetic division, but I'm going to use the long division just for practice. No placeholders needed here. So x times x would give us that x squared. So multiplying, I would have x squared minus 3x, and I subtract So when subtracting, we would get 4x, bring the minus 2 down. And I think what times x would give us 4x? That would be plus 4. Now I'm actually done. I figured out what this is going to be 4. But the reason, I'll just go over the reason why this ends up being the slant asymptote, and I'm going to add a page so that I have more room. If we kept going, so where I multiply, so 4x minus 12, and that would be positive 10. So another way to write f of x would be as x plus 4 plus 10 over x minus 3. So remember how polynomial functions we can rewrite in like factored form. And rational functions we can rewrite by actually dividing. Remember that division bar or the fraction bar represents division between the numerator and denominator. So if we rewrite this and we think about as x is approaching positive or negative infinity, as x approaches positive infinity, this part that represents the remainder when we do the polynomial long division, so the remainder over the divisor, will always end up approaching 0 as x approaches positive or negative infinity, meaning that the function will end up, because it's 10 over x minus 3, and the denominator as x gets infinitely larger, infinitely small, will keep increasing or decreasing without bound while the numerator can't keep up, and so that fraction will end up approaching 0. So the function ends up approaching positive infinity as x approaches positive infinity and negative infinity as x approaches negative infinity in the same way that the line y equals to x plus 4 does. So that's why we're able to say or use this slant asymptote, the equation of this slant asymptote, as a description of the end behavior of this rational function. So to graph the slant asymptote, I'm just graphing a line that has a y-intercept at 4 and a slope of positive 1 in this case. So I'm going to use the dashed because it's not actually part of the graph. It just kind of guides the behavior of the graph. Okay, so that's a rough sketch of my slant asymptote. Okay, so figuring out what the rest of the graph looks like. Well, you can see there's kind of two sections that are created. Well, let's think to the left of the vertical asymptote, it looks like as x approaches positive 3 from the right side, that the graph is going to end up decreasing without bound. And if you wanted to find some additional points, you could. And then as x approaches negative infinity, the graph is going to end up approaching the line y equals to x plus 4. So end up approaching negative infinity in the same way that the line y equals to x plus 4 does. And then to figure out what happens to the right of the vertical asymptote, so basically whether we have points above the slant asymptote or below, I'm going to find what f of 4 is. So just plugging 4 in for x, it looks like I would get, what would that be? 6 times 3 divided by 1. So 18. Oh, that's going to make me go off the graph. So 418. So I would be up here. So if we think about the vertical asymptote extending, the graph is actually going to probably, as x approaches 3 from the right side, approach positive infinity. And then as x approaches positive infinity, the graph will approach y equals to x plus 4 in or our slant asymptote. So the function approaches positive infinity as x approaches positive infinity in the same way that the slant asymptote y equals to x plus 4 does. So that's kind of a rough sketch of this graph. And then working through one more example, I pulled this example from the textbook. Let's use a different color. Use green. Okay, so factoring the numerator and denominator, I'm going to factor an x out of the numerator first. And the denominator factors to be x minus 2 times x plus 2. Let's see if we can factor the numerator further. Okay, so minus 1 plus 1, right? 2x squared minus 2x and plus x. Yep. Okay, so that's what the numerator would factor to. No holes. I can see that x cannot be equal to 2 or negative 2. So the domain of this function would be negative infinity to negative 2, union negative 2 to 2, union 2 to infinity. And no holes, because there's no common factor in the numerator or denominator. But there will be vertical asymptotes at x equals to negative 2 and x equals to positive 2. Okay, and x-intercepts we identify by setting the numerator equal to 0. So at 0, 0, negative 1/2, 0, and 1, 0. Negative 1/2, 0. Oops. Interesting. And then 1, 0. Oh, man. So those are all the x-intercepts. Yeah. And y-intercept, 0, 0. So let's look at end behavior by identifying the end behavior model, which is the ratio of the terms in the term in the numerator and denominator that have the largest exponent. So that ratio would be 2x cubed over x squared, which simplifies to be 2x. And because my end behavior model is a positive sloping line, that tells me that the end behavior is like the positive sloping line, y equals to 2x. And if I want to get more specific, I can identify the equation of the slant asymptote by doing the polynomial long division. Not slant, slant. So I know that the slant asymptote will be at y equals to 2x plus something. And again, to do that, to find the plus something, I need to do polynomial long division. And I need to use a placeholder for the x term. No, put plus 0. I'm just going to give myself one more page for a little more room. So 2x times x squared gives us 2x cubed, and multiplying. Subtract. Okay, and then negative 1 times x squared would give us the negative x squared. And I know once I get that constant, I know I'm done. You could continue if you wanted to rewrite the rational function, you could keep going, but we don't really need to do that. So y equals to 2x minus 1. I'm going to graph that slant asymptote. Slope of 2, positive 2. Okay. Okay, so here is where I can find additional points to see kind of what's happening as the function approaches the vertical asymptotes. So I'm going to plug negative 1 into the function to try and determine what's happening as x approaches negative 2 from the right side. So f of negative 1 would be negative 2 minus 1 plus 1 over negative 3. So 2/3. Negative 1 2/3. So I think that the graph is going to end up, because it won't come back down and cross the x-axis again, but as x approaches negative 2 from the right side, it'll approach positive infinity. And then, because each of the x-intercepts has a multiplicity of, the zeros have a multiplicity of 1, it's going to cross kind of like this. And then it must approach negative infinity. We'll confirm this by checking with Desmos, but we also could plug in 3/2 into the function and see what point we get. Okay, and then figuring out what happens to the left of the vertical asymptotes. I'm going to plug in negative 3 into the function. Okay, so that would be negative 3 times negative 6 plus 1, which is negative 5 times negative 4. If I plug in negative 3, that'll be 5. Okay, so that's 15 times negative 4, which would be negative 60 divided by 5, or negative 12. So down here, negative 3, negative 12. So that tells me if I were to extend the vertical asymptote, as well as the slant asymptote, the graph is probably going to approach negative infinity as x approaches negative 2 from the left, and then it will probably kind of curve, and as x approaches negative infinity, approach negative infinity like that, in the same way that y equals to 2x minus 1 does. And then if I plug in positive 3, would be 3 times 7 times 2 divided by 5. So 42/5, which is 8 2/5. Approximately there. So as x approaches to positive 2 from the right, the function probably approaches positive infinity, kind of like that. And then we'll approach positive infinity in the same, as x approaches positive infinity, in the same way that the slant asymptote does. So that's kind of my rough sketch of this function. And we can double check with Desmos. And that actually looks pretty good. If I were to graph the vertical asymptotes, so x equals -2 and x equals +2. Okay, that makes sense. And the slant asymptote, y equals 2x minus 1. If we were to zoom out, you can see that it looks like the graph of the rational function, which is black, ends up kind of merging, looking like it merges with the line y equals to 2x minus 1, which is green. And if we zoom in, because this is kind of where we weren't exactly sure, but you can see that our graph does look pretty similar. And we knew that it crossed, each of the multiplicities of the zeros was 1, so they crossed. So our graph is actually a pretty good sketch. So these were 2 examples of rational functions that have slant